Our next speaker is Dr. Häuser. You're up.
Okay, good. I thought you were going to say the words, but I didn't.
I'll let you save time by introducing yourself. So.
Okay. Good morning, everybody. My name is Jochem Häuser. I'm from because I like in a pocket's fine. I'm from Germany. I used to work for the European Space Agency. I was the head of the aerodynamics, the aerothermodynamics. Then I went back to university. And what we have been doing for about 10 years is we are looking for the physics of extreme gravitomagnetics and gravity-like fields. These are fields that, according to general relativity, should not exist. We developed some theory based on something that dates back to the 1950s of the last century. And I came across this theoretical work while I was at the European Space Agency, because the MBB, which is a large aerospace company, now it's called EADS, they asked for funding. And we looked at it, and I found it very interesting. I would have funded it, but then the administration decided we only go for chemical propulsion, electric propulsion, nothing that has to do with physics, so no funding. At that time, MBB, now EADS, had a group of maybe 10 physicists working on this subject. When the company was sold, all the physicists were fired, books closed. Now, since we thought this was an interesting thing to do, and I went back to university, we did it. Here we have a couple of publications. But interesting enough, 5 days ago, there's a book by Professor Daigle with the title Gravity 2.0. You can look it up at Amazon. And he reports about the experiments. The experiments mostly have been done by Professor Theimer. At that time, he was at AIT, the Austrian Institute of Technology, but now he is a professor at KAIST in Seoul in South Korea. We did the theoretical work, and I took this picture from the book of Daigle, and this is a sketch of an experiment that we suggest to generate a strong vertical gravitational field. And here is some of the physics. I will try to present some of the ideas. I will skip the mathematics because with every modern physics you have a lot of mathematics involved. But this is not the important point. The important point is the physical ideas. Then once you have the physical model, you can put it into mathematical equations, but one should be able to talk about the physical ideas, the physics behind it. Now, yesterday I heard several phrases: game-changing, we need a breakthrough in propulsion, we need visionary aerospace architectures, advanced and innovative aerospace technologies. Question is, where do they come from? They definitely will not come from engineering, because that will give you an incremental step, but this will not lead to this kind of, I would say, game-changing. We need something like a revolution in physics in order to achieve that. So what is needed, of course, if we are talking about propulsion, we need forces. The previous speaker mentioned a fifth force. We had a fifth force in 1986 by Fischbach, but it turned out not to be correct. So we have to be very cautious in announcing these new novel physics, because most of the time when we announce something, it doesn't turn out to be true. We have had the cold fusion in the 80s, and there have been some other things, the gravitational waves that had been measured, but of course nobody could reproduce. There have been the experiments by Podgletnov that have not been, nobody has been able to reproduce these experiments. So we have to be very careful in announcing novel things. If everything was well with current physics, then we could close the book and would say that there are the four fundamental forces. We have gravitation, Newtonian gravitation, we have electromagnetism, we have the strong force, and we have the weak force. Strong force means atoms exist. Weak force means radioactive decay. Electromagnetism means, well, we have all these lights here. We have the electric engines, etc., etc. Gravitation, we know. Gravitation used to be always attractive. Newtonian gravitation. Picture has been modified by Einstein in his general relativity, but more or less it's Newtonian gravitation. Well, current status of space propulsion. Von Braun's vision of spaceflight, he envisioned a space full of spacecraft and everything. There's a lot of activity here in space. It turned out not to be true. Well, the problem is launch cost is too high. The launch cost is really the main driver. We could have solar energy from space if we could pay for it. The material is not the problem. The problem is bringing up the equipment into a low Earth orbit, and this is the major driver of the cost. So unless we find a different means of propulsion, we will be stuck. This will not become a reality. So what do we have as propulsion? Well, it's easy to say. We have chemical propulsion and we have electric propulsion. My PhD was in electric propulsion. When I did it 25 years ago, we were at 10 millinewton. Now we are 20 millinewton. This is electrostatic propulsion. We have plasma dynamic propulsion. So we are a little higher. But what are we doing with chemical propulsion? Well, it's the same thing as with the Chinese rockets. We are burning fuel, and after 4 or 5 minutes, we throw the whole thing away. It sinks into the sea. 250 million euros are gone when we use the Ariane 5. All this sophisticated technology is thrown away. Then you can think about fusion propulsion, you can think about fission propulsion, you can think about solar sails, all the advanced concepts. The advanced concepts are really not very advanced. If you go to Space Technology 1959, Seifert, or if you go to Corliss, Propulsion Systems for Spaceflight, 1960, all the advanced propulsion concepts of today are there. So the progress that we made has been incremental. The fundamental problem has not been solved, getting a decent propulsion system. Well, here we have Newton. And all of the propulsion systems that we have can be classified because it says it's the conservation of momentum. And this is the rocket principle. We have a physical system that comprises the rocket and the fuel. This is a combined physical system. The linear momentum of this system when the rocket is at the launch pad is 0, and it will remain 0 regardless what you do. We are at maybe 10 kilometers per second. Then Einstein in 1905 with his special relativity said, well, there's another limit, that's the speed of light. So we have the Lorentz transformation, 300,000 kilometers per second speed of light in vacuum. But if you are looking at our recent velocities, 10 kilometers per second, you don't have to worry about the 300,000 kilometers per second. That is the speed of light. Even if you would go at the speed of light, if you have interstellar flight, it would be impossible because it's too slow. So we are not addressing this point here. We are more in this area here. Also, we could say something about this. But first, before we do a giant step, maybe we try to improve in this area here. So the problem is not with the engineering. The engineering is very sophisticated. The problem is the underlying propulsion physics. Unless we are able to change this, there will be no progress. Okay, so we have this is my evaluation of current space propulsion systems. So we have 4 fundamental forces in physics, and if we analyze these 4 fundamental forces, there is no way that you can have a propulsion breakthrough. The question is there evidence for new physical laws? We have heard in the previous talk that not everything is well with current physics. There are a few things that seem to be quite strange. And in 2006, we have seen on the website of the European Space Agency results of experiments. Results of experiments that have been done by Professor Heim that have seen extreme gravitomagnetic fields. When we analyzed what he has measured, we saw that the strength of these fields is far beyond what you get from what we call the lensed tearing effect. That means a rotating body is twisting the surrounding space-time. That has been found out in 1918, but he has a far larger value. What are these experiments doing? He has a 400 gram ring. He operates it at cryogenic temperature, and then he measures the so-called gravitomagnetic field. I will come back to that in a minute. This is an analogy to the magnetic field of electrodynamics. And he measures a field that is 18 orders of magnitude larger than when you do the calculation using general relativity. So there is a certain contradiction. We have the gravity probe B experiment that has been done at Stanford. More or less, they have confirmed that general relativity is correct. So we know what the effect or how large the gravitomagnetic field should be. But we have here a different experiment that says, no, I see something that is 18 orders of magnitude larger. So there is a contradiction. Well, there is more than one contradiction. We have the standard model of current physics. What does it explain? It explains 4% of the matter that we have in the universe. 96% cannot be explained with this model. Quite strange. This is known, dark matter is known since 1933. Nobody has solved the problem so far. It was considered to be not that important because we can explain a lot of other things. We swept it under the rug. Then we saw the dark energy, that is 70%. And this is quite strange that we are explaining only 4% of the matter and energy in the universe. Well, we have developed, I would not say a theory, but a physical model based on something that has been done in the 1950s, 1960s by a fellow called Heim. He was working for the EADS, at that time it was MBB. For 11 years they had some kind of secret project, a group of 10 to 11 physicists. So we got the documents that have been and the papers that have been done during these 11 years, and we added some things and we call it extended Heim theory, but the word theory is not, I would say, a correct description. It's a model. Okay, before I go on with the extended Heim theory, I would like to say something here. So here we have the experimenter, that's Martin Teimer. Martin is, I think, in his 30s. And this is his ring here. You see, this is 15 centimeters, 400 grams. That's not much mass. Here we have Heim. He has developed his theory that extends the general relativity. If you look at general relativity, there is one metric tensor. This metric tensor means you can measure the distances in space. And this metric tensor is related to the gravitational force. So Einstein, for the rest of his life, said, if I have one metric tensor, maybe I can find another one that gives me electromagnetism. At that time, he did not know about the strong force and the weak force. So the question is, can we construct more than one metric tensor to describe all the physical forces? This is the goal. And here is an idea by Heim. He did it. We looked at the work and said, well, the idea seems to be reasonable, how to construct a so-called poly means many, metric tensor for the other forces as well. And then you can do something what is called the geometrization of physics. That means the physical forces have a geometrical background. Well, in Einstein 1915, we say, well, okay, one metric tensor, one force, gravitation. And then there was a strange guy, Hermann Weyl. He was a mathematician. Physicists didn't like him. He always intervened in physics. He had some ideas, and he says, you have external space-time, but there's something invisible space. I call it a gauge space. And the gauge space is responsible for the physics that happens here in space-time. So the space-time to Weyl was some kind of stage where physics takes place, and the internal gauge space that was providing the actors, the particles and the fields. This was 1918. His ideas were first dismissed by the physicists. They said, no, it's not true what he is saying. But in the 50s, 1950s, it was accepted, and it is well accepted today. So we have something that is external space-time, and we have an internal space that has a certain number of dimensions, and both together give you the physical world as it appears right here. This is some common wisdom. So we have here something that is called a Heim space, that is an 8-dimensional space, and from this idea we get this so-called polymetric tensor. Remember, the polymetric means we wish to describe all the physical forces. Well, we were quite surprised when we did this kind of work, because it turned out that you get 6 fundamental forces and not 4. Because you look at the number of metric tensors you get, and you suddenly see there are 6 fundamental forces. So the question is, what are these 6 fundamental forces? How are they related to the experiments? Physics is an experimental science. This is in spite of the fact that we have string theory, which doesn't seem to be related to any experiment. But normally, physics is an experimental science. So we have to have experiments. The proof of the pudding is in the eating. If we cannot have any effects that the theory predicts and that can be measured, it is of no value. So I will be quick, because this is this structure of this internal space, and it is all mathematics. But to summarize, it gives you 6 fundamental forces. This is the result that comes from this external space. Here we have the single metric tensor Einstein, and Einstein could only describe gravity, finished. For the rest of his life, he tried to construct more elaborated metric tensors, but he did not succeed. Then there was the Heim and Finzi. Heim is a German, Finzi was an Italian. In the 1950s, they said we have this double transformation. To our astonishment, when we used this, we found recently in 2009 that the mathematicians have this kind of transformation in their literature, and it's called the nonlinear sigma model. So most of the time you think you have something new, mathematicians already have invented the mathematics but not the physics. So here we get the 6 fundamental forces. You see we have 3 gravitational forces. Gravitation can be attractive, gravitation can be repulsive, and then we have here what we call these particles, the gravitophotons. Because the strange thing is that we have an interaction between electromagnetism and gravitation. This gives you an interaction between electromagnetism and gravitation. The rest remains as it is, except that we have here a few more gluons. And this is a 4D hypercube. So we have the cube in the middle. This is all the ordinary particles that we know. The additional particles that should exist are on the outer cube. These are particle families. And we are using these families, these particle families, to analyze the experiments that have been done by Taima, and then the Australians, Graham, and then we have Gravity Probe B. So we analyzed these 3 experiments. Here it's something, if you have a physics background, you can see what the so-called gauge particles are. We have here 6 gravitational gauge particles. We have a repulsive gravitation that we think is responsible for the dark energy. And we have here the 3 photons. This is a normal photon. These are 2 additional photons, and these are responsible for the interaction between the electromagnetism and the gravitation. What does that mean? It means that we can convert an electromagnetic field into a gravitational field. Well, what is the evidence for that? Okay, here we have one thing that is very important in physics, symmetry breaking. Without going into the details, everybody of us knows superconductivity. At a certain temperature, suddenly a material becomes a superconductor. That means resistance is 0. And this temperature, this special temperature, we say in physics, a symmetry has been broken. But we see there is a drastic change in the behavior of the material. A drastic change in the behavior of the material. And the same thing happens in Taima's experiments. At a certain cryogenic temperature, which is different from the temperature of the superconductor, he uses niobium, suddenly this strange extreme gravitomagnetic field sets in. So for us, this is a hint that we have the so-called symmetry breaking here, and this tells us how to model it mathematically. Then there is another point, conservation laws. If you do physics, you are doing conservation laws. If you do away with conservation laws, you are doing voodoo physics that doesn't make any sense at all, because you can prove anything and everything. But the question is, if we wish to fly without propellant, how can that physically be done? How can we do it? The idea is, suppose you are in a boat and you wish to move the boat. You are on a lake or on the open sea. Then you have a pile of bricks in your boat and you throw the bricks. Okay, so the boat moves in the other direction. You would say maybe it's not the smartest way to do it. If I have a rowing boat, I can row. I don't need the bricks. So what is the difference? The difference is that you impart momentum on the surrounding ocean. So the ocean and your boat are the physical system. In the other case, the bricks and the boat is a physical system. So what does it have to do with rockets? Well, a rocket, you have the rocket itself and the fuel. This is a physical system. So what we want to do, if we wish to do without fuel, we have to have space-time and the rocket acting as a physical system. That means the second case. So if we can impart momentum onto space-time, then the spacecraft should fly. And this seems to be the case in the experiments that Timer has been doing. I will skip this because I think I'm running out of time.
Let me say something quickly. I'm going to give you more time, but I just want to say that Ben Solomon, who's the last speaker, hasn't shown up. So, and I gave Mr. Reed about 10 more minutes. And so would you speak for about 10 more minutes? And,
yes, if the audience can bear for that long. You see, now we are coming to the experiments. We have to relate the theory to the experiments, and then the conclusion must be, what is the technology that we can get out? All these three things have to come together, otherwise we will not be successful. We have had experiments by Podglednov, and there have been several papers, but I have talked to the head of a group from England who had Podglednov as an advisor for a consultant for 3 years. So they said, we don't believe that these experiments are real. They did it for 3 years. They did everything. What he was telling them, it didn't work out. They redid the experiment a couple of times. It never worked. So after 3 years, it was paid by British Aerospace under Project Greenclaw. They stopped and said no. There is nothing that we can do. Then there were theoretical physicists, Lee and Thor, that said, yeah, we have a proof that these experiments are correct. Then there is the well-known Harris from the University of, I think it's Mississippi. He has shown that these papers, they all had been published in scientific journals, are incorrect. So there is nothing that we can trust. So here's a paper where Harris has shown these fields, according to general relativity, do not exist. You cannot use general relativity to generate extreme gravitomagnetic fields. It's no way. It does not work. So if we cannot do it with general relativity, maybe we can extend general relativity. Now we have a ring here. Now we are looking for the real Lord of the Rings because, well, this is a ring of power. So we have experiments here, and you see here is our ring that we have in the experiment. If I look at the gravitomagnetic field of this ring, we did the calculation, an astrophysicist told us, why don't you compare it with a white dwarf? And we calculated the field of the white dwarf, and it's almost the same size. But look at the mass of the ring, it's 400 grams, and here we have a rotating white dwarf. It's more than strange. Either all these experiments that have been done are wrong. There is a possibility that they are wrong. Or there is something that is really important and we should have a close look at it. Because this means generating a gravitational field not by having a big mass sitting somewhere or rotating the whole Earth. It is extremely difficult to measure a gravitomagnetic field. The Stanford people, together with NASA, used the whole Earth for a period of 10 months to measure the effect of the rotating Earth with regard to the surrounding space-time. I'm not sure that this experiment was a success. I won't say anything more. It took 50 years. The cost was $1 billion. But here we have somebody, he doesn't measure for 10 months. He measures for a few seconds. He has a mass of 400 grams and he rotates the ring. This is a totally different principle to generate a gravitational field. Okay, here we have the first publication in 2006. I have talked to Martin a couple of times, so he redid the experiments, but here are the results. And we have another group, Graham et al. From Australia. They said, we have seen nothing conclusive. If you look at the last row here, they are using a lead disc, and this is a niobium ring. So it's the same principle. Measurement is totally different. They have a laser interferometer that's 40 times 20 meters. And you see, they have, this is clockwise. You rotate the disc clockwise or you rotate it counterclockwise. You get here the so-called gravitomagnetic field strength. It's 37 plus minus 13. This is not within the 5 sigma rule. That means a measured value or the standard deviation. This is a standard deviation of a measured value must be only 20% of the measured value in order to have a correct or credible measured value. The problem is with the equipment that they have, they cannot do it. But the interesting thing is, Timer has seen some kind of parity violations. That means if you rotate clockwise and if you rotate counterclockwise, you see completely different field strengths. And they see the same thing here. So regardless how exact they measure, because this is not exact, if the value is -5 and the standard deviation is 8, you cannot say I've measured something. This is quite clear. But the interesting thing is we see in both measurements you see the parity violation. Then we have the Stanford Gravity Probe B experiment. I mentioned that, measuring this gravitomagnetic field. And here you see there is a satellite in orbit. And because the Earth has a certain mass, and you have a gyro, or a gyrometer, its axis of rotation is moved in the plane of the orbit because of the mass of the Earth. That is called the geodetic effect. This is an effect from general relativity. And then the Earth is rotating. It has a spin. And then it moves this spin. This is called the Lense-Thirring effect, 1918. It moves the axis of the gyrometer out of the plane of rotation. So they wanted to measure both, but they did not succeed very well in measuring this effect, because a strange thing happened. In this experiment, the gyros are niobium spheres, small niobium spheres. They are rotating, and then, because the conservation of angular momentum, the direction of the axis of rotation remains unchanged, unless you have a torque that really changes the direction of the axis. And this was supposed to be the Lense-Thirring effect that they wanted to measure. But suddenly, they had 4 of them. They operated these niobium spheres at the temperature of liquid helium. If you remember what Timer did, he did the same thing, but he saw very strong gravitomagnetic fields. That means if this effect exists, then there is an interaction between the 2 spheres. And this will ruin your experiment, because this effect is 100 times larger than the Lense-Thirring effect that you want to measure. So we published a paper. Here we calculated the minimum and the maximum effect, and this is what they have seen in the gyros here. We talked to some of the Stanford people, but well, they told us if you wish to analyze the data, you have to pay us. So, well, that's not what we had in mind. I'm not saying that we are correct, but I say we expected something like this. They have a different explanation. They say it's an electrostatic patch effect. I will not go into the details, but I think there might be room for both effects. So, because the problem is, if this is true here with the gravitomagnetic fields, the experiment was ill-conceived from the very beginning, because you never could have, you cannot see this Lense-Turing effect very accurately if it's overlaid by an effect that is 100 times larger. We calculated, this is what the measurements, the experiments measured, and we calculated something like this. So, from our theory. We also did the analysis of 5 experiments. So these are the theoretical values that we calculated. We are not using any experimental parameters, and these are the measured parameters. So far, there is coincidence. You can say, well, it's by accident, but I don't think so. The gravitomagnetic phenomena that we have cannot be explained by the 4 fundamental forces. If these experiments are right, there is no way that the 4 existing forces can explain these experiments, because we only have 2 long-range forces, electromagnetism and gravitation. Taimer said, I completely shielded the electromagnetic field. So the range of the weak force and the strong force is 10 to the minus 15 meters. We measure the field several centimeters away from the ring. So this is a long-range effect. So we have to exclude the weak and the strong force. The electromagnetic field has been shielded, remains only the gravitational force. But we have enough evidence now that says this gravitomagnetic field cannot be explained by general relativity. We have theoretical analysis, and we have experiments in the form of the Stanford Gravity Probe B experiment that clearly says, no, general relativity is correct. So we have a strong contradiction here. What is the conclusion? Well, if the 4 forces cannot do it, there must be other forces. As we have seen, what Taimer has measured and Graham have measured must be a gravitational field. That means the nature of gravity cannot be the simple Newtonian attractive force. There must be something more. It must be more complicated. And it must be a force. So I've written here the conclusions. That's like a detective. Sherlock Holmes does it okay. Who is the culprit? And for the existence of the extreme gravitomagnetic field. So it must be a new gravitational force, if this experiment is correct. Now we set up to come up with a physical model, and I'm not going into the details, but the Einstein field equations, if you linearize them, they become the so-called Einstein-Maxwell equations, because they look very close to the electromagnetic equations. And it has been surmised for many years, if these equations are so similar, maybe there is an interaction between the gravitation and the electromagnetism. We have modified these equations because in the Einstein equations, you must have a so-called current density. The current density, if you have masses, is just a moving body, the mass of a moving body multiplied by its velocity. There's no way that you can use this type of equation, because then you're back to general relativity. The fields that you get out are far too small. So now we say the current density is really a current that is generated in the ring. Add the symmetry breaking, because the symmetry breaking means you go to a low cryogenic temperature. Something special happens similar to superconductivity, but not the same. And if you look at the way people explained superconductivity in 1935, they had no idea about the BCS theory, which is a quantum theory of superconductivity. They simply said, it was the London brothers, they simply said, superconductivity means resistance is zero. What is needed is we have to supply an additional equation that accounts for this fact that the resistance in the material is zero. Then we add the electrodynamic equations, and then we can calculate. So we're doing something similar, except we are not using the electrodynamic equations, we are using the modified Einstein equations, but here you have to make sure that you have the right source term, which comes from electromagnetism. So we have a coupling here between electromagnetism and gravitation. And then, as I said, the momentum principle is an important principle. You have a physical system in this experiment that is the surrounding space-time and the ring. That is a physical system. If you analyze your momentum, you have to analyze the momentum of the space-time plus the rotating ring. With regard to propulsion, that would mean spacecraft and space-time, the momentum has to be analyzed. Now, when we did all this analysis, we said, Taima has measured an acceleration field, so he rotates his ring. He measures an acceleration field in the plane of the ring. You see? That is, in the plane of the ring means you have no component along the axis of rotation. And the field seems to counteract its origin. That's like a lens rule in electromagnetism. And it seems, if you do the analysis, if you modify the experiment, that you can, instead of having a field in the plane of rotation, you can have a gravitational, an acceleration field along the axis of rotation. You have to modify the experiment. So we have here a sketch. I'm not going into the details because we are running out of time, but here we have calculated something. And I think the numbers that we have technically doesn't seem to be so difficult to do. And we have calculated here that with the coils that we have, we need a coil, an additional coil. So we should see a strong, really a strong vertical field. This is, of course, theory, and there may be effects that reduce this acceleration field in the vertical. But the important thing is the theory clearly says there should be a measurable effect. It's the same theory that we have used to analyze the 5 experiments. So we have used the same principle for the field that says we should be able to generate a vertical gravitational field. This is what the theory says. As I said, the proof of the pudding is in the eating. We have to do the experiment. The problem is you have to have experimenters that know how to work with liquid helium. That's the important point. Now, last thing is, if you look at energy generation, we had high hopes for fusion. I was working in this field for a while, and we always said 20 years from now we will have it. That was in the late 80s. But now we say 30 years from now we will have it. But we will only have, with the ITER in Cadarache in the south of France, we will only have an ignition facility. We will not have a reactor. The problem is the plasma instability. That's the physics problem. quench the plasma and it tries to do something else. It becomes unstable. We have kink instabilities. We have a lot of instabilities in plasmas. So suppose now, and we have a tokamak. A tokamak is a donut. The most expensive donut is being built in the south of France. It's 14 billion euros. Maybe it's about $18 billion. And I think in the end it will be twice that amount of money. And it is an ignition facility. And we have to run the plasma for a year. We have done microseconds. And we have to pre-tritium, which is very difficult. So, yeah. And I will be wrapping up. So the problem is with the tokamak, because that's a circular configuration. So we have additional forces if we drive the plasma around. This thing here is a magnetic mirror, and in principle, if you look at the theory, it says, the particle should be here on the green trajectory, and when it is here, it should bounce back, so it keeps inside. But the problem is the Lorentz force is 0 along the axis. So the particles that are moving along the axis, they can escape. Now, the leakage here, of course, is the major problem. After a certain time, your fusion reactor will have no plasma anymore. Idea is, suppose now we can generate vertical gravitational fields, and we use 8 of these gravitational fields to drive the plasma back, because the gravitational field acts on the electrons and on the protons in the same way, in the same direction. So you can drive them back. And at the same time, you would be able to heat the plasma. That is just the idea. The question, of course, is how large do the fields have to be? So you need some computer simulation to do that. But it is an idea. So we are spending $18 billion, and most likely it won't work. To wrap up, we have clearly seen if the experiments that we have been discussing on the extreme gravitomagnetic and gravity-like fields are true, the 4 fundamental forces that we have at the moment, physics believe that we have these 4 fundamental forces, are not sufficient. Cannot explain these fields. A clear contradiction. Let me skip this one. And coming to the last slide, I said, well, what should we do? And the first thing is, of course, we should try to reproduce the experiments by different groups. And second, we should have a close look at the experiments that we are suggesting, namely having a vertical gravitational field. And then, of course, we need a joint theoretical experimental program. But if you look at the amount of money that is being spent now on fusion ideas in other areas, here this would be $2 to $3 million. This would not be a large investment, but the benefit could be enormous. Because if you have something which I call gravitational engineering, that really could change transportation energy generation completely. The technology is not very difficult. The physics is more difficult. But once you have understood the physics, the resulting, the ensuing technology is much simpler than rocket propulsion, etc., etc. Okay, here I stop now. Thank you very much.